Excuse me. Yeah. So in the previous class, I have just given you some glimpse of what we mean by turn-off methods. When you are looking for turn-off, turn-off mechanism or turn-off methods, it is mainly concentrating on the thyristor. We may be using a thyristor in our circuit. Thyristor will be triggered. At some point, we need to turn off that particular thyristor. So, how to turn off that particular thyristor which is there in the circuit? We will be having a circuit, we will be having different elements in the circuit itself. Very basic components like resistor, capacitor, inductors, and any other components. Along with that one, we are using a thyristor in our circuit. Initially, it will be off state, and with some gate current, we will be turning on the thyristor in the circuit, so that it will become a forward bias. It's going to operate itself. And as we all know that one, it will not turn off the thyristor. It will not turn off by itself. It needs some process or some mechanism to turn off the thyristor. So we have to concentrate here how exactly we can turn off the thyristor. The question raises here is why we need to turn off the thyristor. Already on, it's in forward bias, it's working. Why need to turn off that one? We know that for our power electronics system, there are basically two different types of methodologies like AC circuits and DC circuits. AC circuits operates differently. DC circuits, the requirement of the DC circuits are more currently. Almost all electronic gadgets they are using the DC current itself. So during AC circuits, we may be using the thyristor, the operation is going to be different. During the DC circuit, we are going to use the thyristor, the operations are going to be different itself. Sometimes we need to go for switch off or turn off the thyristor, because basically it says that once it is turned on, once the thyristor is turned on, we will not have any control on the thyristor. It will be in the forward bias only. So we need to, because I need a DC voltage or I need a DC current, there should not be any fluctuations. So I have to control the thyristor. I'm supposed to control the thyristor. So we have to deal with the thyristor mechanisms. With respect to that, when you look into the syllabus, I'm still in the first part only. See there is a turn-off methods. Or before that one, turn-off mechanisms. Turn-off mechanism. See here, turn-on methods, we have checked it. Turn-on methods. Turn-off mechanism, it is clearly mentioned in the textbook. What we are using is the textbook 2.3 and 2.6. In between 2.4 is there, 2.5 is there, we are not using. Okay. And even 2.6 also, without 2.61, there is one component, sub-component in the subtopic, we are supposed to not to touch that. And 2.7 and 2.9. So these are the topics we are supposed to concentrate, and these are definite questions in the examinations. Okay, turn-on mechanisms, what are different types of turn-on methods and different types of turn-on mechanisms, how exactly they are going to work. So we will go for these topics, and we should look into how the circuits are going to play an important role when you go for a turn-off mechanism and turn-off methods also. So based on this, I'll switch over to my slides. Turn-off methods. The commutation is basically the transfer of current from one path to another path is known as a commutation. I think it's visible for you people also. Okay. Commutation means what? It is the current is flowing in one direction, in one path. You have to change it to another path itself. The process of transfer of current from one path to another path is known as a commutation. Okay. So when you go for transfer of current from one path to another path, your SCR gets some mechanism, it's getting affected, and your control is going to be reduced over there. The control or the process, the operation is going to be changed. In thyristor, this term is used to describe process of transferring current from thyristor to another thyristor. Basically, what happens? We will be having a circuit, we will be having some components. The current is flowing in one direction, one path. We may change that one to another path. That is what commutation. But when you're using a thyristor, the process of transferring the current from one thyristor to another thyristor is called as a commutation. That is the difference. Basic definition is changing the path of a current. But when you are looking into the thyristor part, changing the current or transferring the current from one thyristor to another thyristor. As explained earlier, it's not possible for a thyristor to turn off itself. Thyristor cannot turn off itself. That's what we are in the previous class also. We clearly mentioned that when I projected the slide, it is clearly said that when self turning off is not possible by the thyristor, it will not turn off by itself. Okay, we need to have some external circuit to turn off that one, or we need to have some external force to turn off that one. So basically, we are going to use external circuit to turn off that. A circuit in which the thyristor is connected must reduce the thyristor current to 0 to enable it to turn off. What do you mean by that? We need to have some circuit, some type of circuit, a basic circuit, set up some basic components, which says that when it will try to send a zero current, it will try to send a zero current such a way that one that the thyristor can go to the turn off state. Initially, it is like some current, gate current we have passed. So based on the gate current, the thyristor is switched on, triggered, or what we can call firing angle. If you are using one more circuit, it will make it ensure that when the thyristor current is going to be reduced to 0. Once the thyristor current is reduced to 0, your thyristor is going to be turn off status. Commutation is the term to describe the methods to achieve this. So whenever there is a definition asked for what do you mean by commutation or define a commutation, so you can mention that when commutation means it is like the path from one circuit to another circuit, or one thyristor to another thyristor, or one path to another path. Everything is you can give that. Any doubt here? It's a simple explanation. Okay, what do you mean by commutation? What is the purpose of commutation? And in the thyristor case, what we are going to use that? Okay, fine. We come to know what exactly commutation and what exactly a thyristor will take care. What is the limitation of the thyristor? We come to know that. Now, how to turn off that? How exactly we can turn off the thyristor? So we said there should be external circuit. There should be an additional circuit which can turn off the circuit over there. Let us see how exactly we can turn off that. Commutation is one of the fundamental principles, the use of the thyristors for control purpose. So whenever you want to control the thyristor, commutation is the first fundamental principle. Means we are going to use the commutation. Any operation or any controlling has to be taken care with respect to the thyristor. We go for a commutation. Basically, the thyristor can only operate in two modes, either in off state or on state. We know that any device, it can work on off state or on state. Thyristor also same thing. If it is off state means what? It is open circuit. If it is on state, it is closed circuit or short circuit. Short circuit, you might have heard about that one. It is shorted. Okay. Open circuit, that is off state, it is off. Closed circuit or short circuit, we call it on state itself. Control can only be achieved by variation in the time thyristor when switched on and switched off. So what I have to do? The thyristor time on and time off, you have to vary that. Vary the time of the time on, vary the time on and time off of a thyristor, such a way that when you can control your thyristor. Thyristor is switched on. Thyristor is working. I given the gate current. It's keep on going over there. It's going beyond the control. But how to control, how to apply the commutation means time on and time off will be there. No, that time intervals you have to change over there. If you change them, then it will be easy for you to control your thyristor. Control can only be achieved by variation in the time thyristors when switched on and switched off, and commutation is central to this switching process. Means once again he has given a different statement saying that when it is commutation is the process where you can control your thyristor on and off state. All thyristor circuits involve the cyclic or sequential switching of thyristors. All thyristors, what are the thyristors we are having? Different types of thyristors. They will involve the cyclic or sequential switching. Either I can go for the cyclic switching or sequential switching. Okay. Heard about cyclic or sequential? Sequential, you might have known that. What do you mean by sequential? One after the other, you are going to get that one. Cyclic is this on, off, on, off, on, off. That is what the difference. It's like a positive, negative, positive, negative, positive, negative. That's cyclic. There are, assume that one there are 2 or 3 thyristors are there. When one is on, second one is off. When second one is on, third one is off. So like this, we are going to get the cyclic over there. Sequential is one after the other. Sequentially we can switch on and switch off that one. So either you can go for cyclic or you can go for sequential switching. Now let us see what are the different types of commutations are there to switch off or to control your thyristors. Any doubt here? It is whatever is there in the syllabus as it is. I'm explaining. I'm just giving meaning how exactly it's going to work over this. Next. Basically, there are 2 types of commutations. There are 2 types where we can control the thyristor, where we can switch on or switch off the thyristor over there. Those 2 methods are called, one is natural commutation and second one is the forced commutation. Naturally, it has to commute. Naturally, the current path has to be changed. Other one, forcibly, means some force, we are going to apply some force when based on that, the current is going to be changed over. The current path is going to be changed from one place to another. Let us see what I mean by natural commutation and forced commutation. Simple natural commutation is naturally it is happening on its own. Naturally it's happening on its own, but thyristor itself will not do. Thyristor itself will not go for switched off state or switched on state. We should have some external force to either switch on and also switch off. Thyristor, if you want to switch on, gate current has to be given. Externally, we are giving the gate current. Thyristor, if you want to put into thyristor off state, external circuit has to take care of that. So now, natural commutation is simple and most widely used. It's a very simple method to control your thyristor, to switch off your thyristor. Most suitable and most widely makes use of alternating, reversing nature of AC voltage to affect the current transfer. So what happens? AC voltage is there. AC voltage means what? It will go for alternate voltages. It may be positive, negative, positive, negative, positive, negative voltage you are going to get. Just like AC voltage, what we are given in your rectifier circuit, what we are given. In AC voltage we are given alternatively keep on giving the AC voltage. Once you apply the AC voltage, what's going to happen? In AC, the current always passes through 0 every half cycle. Every half cycle, the current what you are giving, AC current means what? 0 to maximum, maximum to 0, 0 to negative, negative to 0. So every half cycle, whatever the current you are passing through, it will be crossing the 0 by naturally. Naturally, it is crossing. It is not we are forcing over there. AC current itself is there. The nature of the AC current is that only. AC current what it will do? For the first half cycle, go positive and come back to 0. Then the second half cycle, from the 0 start, once again go to negative, maximum, then come back to 0. So in AC, in alternate current, the current itself is not forced by anyone, not forced by the circuit, not forced by any device connected to that one. By nature, it is crossing the 0 for every half cycle. So as the current is going to the 0, the voltage across the thyristor is getting dropped. It is forcing or it is ensuring that the thyristor voltage is getting dropped over there. Once the thyristor voltage is getting dropped, automatically thyristor is going to be in open circuit. Simple. Okay. So as the current passes through the natural 0, a reverse voltage which simultaneously appears across the device. I'm going up, keep on moving up. Okay, up to maximum is done, then comes back 0. As it going to 0, then the reverse voltage appears there. As it reverse voltage appears, obviously the thyristor will be going to the off state over there. this immediately turns off the device. Getting what I am telling? So if I don't think need to write a waveform and explain, keep explaining over there. The statement itself is telling that one AC current naturally it is going for 0 to maximum, maximum to 0, 0 to maximum, maximum to 0 in both the direction. So each and every time when it comes to 0 current, a reverse voltage appears over there. Once the reverse voltage appears, it automatically, naturally turns off the your thyristor over there. So it is natural commutation, no external circuit is required. Getting understood what exactly natural commutation means? It is purely based on the AC current. Purely based on the AC current which you have applied to the circuit. I'm not having any external circuit for this one. I'm not creating any external circuit. Just a thyristor is connected with your input voltage or input current. Input current is a AC current. It's keep on varying. So thyristor will be switched off each and every time when your current goes to 0. That is natural. Okay. The second method is forced commutation. As the name itself is saying that when it is forced, we have to force. We should ensure that it's like a reactive. It's always reactive. Depending on the external circuit which is connected, depending on that, the thyristor may go to switched off state. May go to switched off state. I want generally the thyristor is working in the on state, but I need to switch off that one. Either applying in AC circuits, almost all AC circuits, they're using AC current. So automatically, naturally, they're going to use that one. Whenever you're applying the AC current for your circuit, if the thyristor is there, automatically it will be going for the switched off state. But whenever you go for the DC current, assume that it's a DC circuit. In DC, what happens? I will be giving positive 5 volts. Positive 5 volts only I'm giving. I'm not reducing that one. Okay. It is positive, constant 5 volts I am giving. If I am giving a constant 5 volts, it will not cross 0. It will never cross 0. So there is no voltage or current which is crossing 0, which will not initiate or which will not trigger your thyristor to switch off mode. At that time, I need to use an external circuit where it will force your thyristor to go for switch off. Okay, so we'll see what is the external circuits we are going to have. Understood about natural commutation? Forced commutation. Once the thyristors are operating in the on state, carrying forward current, they can only be turned off by reducing the current flowing through them to 0 for sufficient time to allow the removal of the charger carriers. That's what. Thyristor cannot turn off itself. That's a single state. That has been elaborated in the paragraph. Thyristor, if it is on, it itself naturally it cannot go to 0 or off state. You have to ensure that there should be force. In case of DC circuits, clearly it's mentioned, for switching off, the forward current should be forced to be 0 by means of an external circuit. So natural commutation, no external circuit, but in your forced commutation, there should be an external circuit, you have to use that. The process is called process commutation and the external circuit is required, known as commutation circuit. Basically, the commutation circuit may involve or may include some capacitors or some inductors, some other components where we are going to design the commutation circuit. That commutation circuit will take care of how exactly we can force your thyristor to switch off or turn off. The reverse voltage developed across the device by means of the commutating circuit immediately brings the forward current in the device to 0, thus turning off the device. So whatever the external circuit you are going to design, okay, the reverse current is going to be developed, the reverse voltage will be developed in that particular circuit that forces your thyristor. There is a reverse voltage which is developed in my circuit, which will naturally it will go for the reverse current. That reverse current will say that one. It was initially it was plus 5 volt. A reverse voltage has been developed that will naturally says that one there is a reverse voltage across my device and my circuit, so there is a reverse current flows over there. That reverse current means it is going crossing the zeros. It is crossing the 0. By nature, DC will never cross. By nature, DC will never cross. AC will cross zeros, but DC current will not cross. So we are creating an external circuit that external circuit will ensure that when there is a reverse voltage is going to be developed. In turn, the reverse voltage will create a reverse current. As soon as the reverse current comes, it is crossing the zeros. Obviously, your thyristor will go to switch off mode. So current in that is brings the forward current in the device to zero. Thus, whatever the forward current was there, that will become zero. Initially, it was forward current, it's in the positive side only. Since the reverse voltage is developed, that will go to zero. That will create a forward current is reducing to zero. Once it crosses zero, your thyristor will turn off. This is forced commutation. Producing reliable commutation is difficult to be tackled while designing chopper and inverter circuit. So obviously, what happens now? We have learned theories. We have come across what do you mean by natural commutation, what do you mean by forced commutation. But where exactly they are going to be used, and how exactly we have to design them? It's very, very important. See, theoretical knowledge is okay, but if I want to go for reliable commutation, my DC system is there. Assume that when my laptop or mobile, I'm charging. Okay, I should ensure that when there is a reverse, there is a thyristor is going to be turned off. Simple example I can tell you. A mobile, you're connected to a charger. It is almost fully charging. You kept it for charging itself. At some time, it should say that when it is fully charged, now I don't want to charge my mobile. Automatically, you can turn off. Charging can be turned off there itself. Overcharged, I think you may be having overcharged mobiles where your battery will get bumped. It's going to become thick in size, so you're not supposed to overcharge that one. There are some chargers are there where once your device is getting charged for 100%, it will turn off the charging itself. Where it's going to be, the current is going to be reversed. Where your thyristor, which is there in that way, it's going to become turn off, so no current flow comes into picture. Your device will be safe. It is some example. So where exactly we are supposed to use? We are going to use designing choppers, DC to DC converters. That is DC to DC converters only, choppers, and inverters, DC to AC converters. We already discussed in long back. So whenever you are designing the DC to DC converters and whenever you are designing the DC to AC converters, that is inverters, you are going to concentrate on how exactly a forced commutation comes into picture. The most important stage in the designing process is choosing the forced turn-off methods and deciding components. As we know that capacitors should be used, inductors should be used, okay, and you should know what should be the value of the capacitor, what should be the value of the inductance, so that it will ensure that when there is no harm in my regular circuit, regular design, and my thyristor should be turned down. Should be done. So very, very important is type of the methods, turn-off methods you are going to use, and also the type of the components you are going to select and the values of that components what you are going to use. Capacitance value, inductance value. We have even in labs also we have checked. Now what are the experiments you did? Half-wave rectifier, full-wave rectifier, Clipping clamping, you did that. And there is one capacitance, 47 microfarad we have used over there. Half-wave rectifier, and that one filtering circuit we have used over there. Half-wave rectifier will be full-wave rectifier, we use 47 microfarad. And there is some clipping clamping we have used. In that one, 0.1 microfarad we have used. Capacitance. A silicon-based capacitance we have used over there. In the other case, we have used the electrical capacitance. In one type of the circuit, we use the silicon capacitance. In another type of the circuit, we have used the electrical capacitance. Electrolytic capacitance we have used over there. Means the values are very, very important. If it is a small capacitance is required, then we are going to use the silicon capacitance like 0.1 microfarad, 1 nanofarad, 0.1 nanofarad, 100 nanofarads. At that time, we are going to use the silicon capacitance. But when you want to go for the microfarads, like 100 microfarad, 47 microfarad, 1 microfarad, at that time we are going to the electrolytic capacitances. Because selection of the capacitance is very, very important, where you are going to ensure that there is no harm for my circuit and it's going to take care of the thyristor turning off and turning on both. Now, this is what two different types of commutations. And designing is very, very important. How exactly we can design our circuit? So there are basically 6 different classifications are there. Class A to class F. But as per the syllabus, we have only 2, class A and class B. Class A and class B types only we are having in the syllabus. So they have referred 2.10 without design consideration. So 2.10 is the topic in your textbook. We don't want to consider the design. We should not consider design over there. Just how exactly a circuit is going to be there. No need to go for digging out the design itself. Just we are going to write the circuit and circuit will take care of how exactly a commutation will be done for your thyristor. So basically, as we all know that there are 6 different classes are there for commutation, that is force commutation. But out of that one, only 2 we are going to use. One is class A, other is class B, and that too we are not concentrating on the design consideration. We don't dig out how exactly it is designed. What are the design parameters? We will not go for that. Let us see one by one. Okay. Class A, self-commutation by resonating the load. Its load actually is extra character it is there. Self-commutation by resonating the load. Second one is also self-commutation by an LC circuit. One is resistor, other is LC circuit. We are going to use that. That's what they have told in the first statement itself. Either you can use the inductor or capacitor or LC or combination of LC for forced commutation for your turning off your thyristor. To turn off your thyristor, either you can use the load or you can use the LC circuit over there. Let us, and other things, just for the information I have noted down. Class C, complementary commutation. Class D, auxiliary commutation. Class E, external pulse commutation. Class F, AC line commutation. AC line, generally what happens? It is naturally it's going to do. Natural commutation is going to be. That is AC line. AC line is keep on changing over there. Naturally, it's going to cross 0, so AC commutation comes into picture. But other things, these things, self-commutation by resonating load, self-commutation by LC circuit, self-commutation by complementary, that is SCR, capacitor by a load carrying SCR, class D, commutation and auxiliary SCR switching a charger capacitance. So these things, it is self-learning. They are not there in the syllabus. But what I can do, what you can do, you can design those circuits. You can just go through those topics when you're free. Spend some 10 to 15 minutes. Note down the circuit, those circuits over there. Note down the values of those components, and you can execute them in the lab. You can execute them in the lab so that you will come to know how the thyristor is working. How your thyristor is working, like whether switching on, switching off, switching on, switching off, it's going to work over there. It's a self-learning process. It can be given as a beyond the syllabus questions. It is not the theory you have to do. Practically, you should expose into that one. Practically, you should check that one. If I am using the LC circuit, if I am using the L value and C value, how exactly my thyristor is going to work? My SCR is going to work. I can give the SCR component, I can give the LC circuit, rig up the circuit and execute that. See to that. We don't know. Theoretically only there is explaining over there. You can explore yourself and it may be a mini project for you also. All these 4 types or all these 6 types you can do in lab whenever you find free time. One breadboard, 4 components. That's all. Okay. A DC voltage we are going to give for the DC voltage and thyristor and LC circuit. Almost 4 components. Maybe you may need some resistance, some resistor as a load. You can go for it. So let us see one by one. Class A, Class B, Class C. No, Class A, Class B only. I'm finding lot. Close.
Okay. See, in the yesterday's class, there was some spelling mistake was there. Without my notice, it has come. It is not natural communication, it is natural commutation. Okay.